Let me introduce our next speaker, Kostiantyn Tolmachov from University of Edinburgh. And the title of his talk is Link Invariants and Character Sheaves. Please.
Yes, thank you very much for having me. It's a great pleasure to be speaking at this conference. I thank the organizer for giving me this opportunity. So everything I will be talking about is based on joint works with Roman Bezrukavnikov, separately with Yakov Varshavsky and Andrei Ionov. And time permitting, I will also speak on some work in progress with Kwok Ho, Andrei Ionov, and Penkui Li. So let me start with a reminder about the Homfly-PT polynomial. So Homfly-PT polynomial is a certain link invariant that can be attached to any oriented link. And the way it is done is shown on the board. So you start with the link oriented link diagram, and you apply a certain recursive relation to it called skein relation. So you can replace any crossing in your diagram with another crossing and an uncross, and the polynomial will satisfy a certain recursive relation marked by star here. And then you normalize your invariant so that on an unknot it is equal to 1. And then it is known that this recursive relations gives you a well-defined invariant on any oriented link. So in 80s, Jones gave another interpretation of this link polynomial that has a more algebraic flavor. So to do this, you first start with invariant that is defined not on links, but instead on braid groups. So you consider like collection of braid groups for on n strands for all n, and for each group you define certain functional Pn of beta, which I will talk about in a moment. And then to recover the Homfly polynomial, you take your braid, you close it up to obtain a link, and the invariant is given by this functional computed on the corresponding braid. And it is a theorem that the result does not depend on the braid if the resulting link is the same. Okay. So the skein relations, recursive relation shown on the previous slide, shows that this invariant Pn actually factors through the Hecke algebra Hn of symmetric group. And I recall what this is. So it's a certain unital algebra defined over the ring of Laurent polynomials in variable v. It has the same generators as a braid group, T1, Tn minus 1, and certain relations. So the first two relations are the same as in the braid group. So these are called braid relations that should tell you how to deal with adjacent braids, adjacent crossings, and crossings that are far away from each other. And one additional relation called the quadratic relation. So it tells you what happens if you square the crossings. This one is not, of course, present in the braid group. So immediately from this presentation, you see that Hecke algebra of symmetric group is a quotient of the group algebra of the braid group over this Laurent polynomial ring. And it is also, you can also see that if you specialize V to 1, this algebra specialized just to the group algebra of the symmetric group, because the quadratic relation just becomes the relation Ti squared equals to 1. And so the theorem of Jones mentioned on the previous slide tells you that there is a certain collection of functions on the Hecke algebra, on the Hecke algebras now instead of the braid group, and a certain change of variables that I would not that I will not specify. There are many different choices of variables in this business. So such that to recover the Homfly polynomial of a braid and of a link, you need to compute this Jones trace, or it's also sometimes called Jones-Ognanu trace, on the projection of your braid to the Hecke algebra. So one immediate remark is as follows. Again, we wanted in the beginning to define a link invariant. So this functional on the Hecke algebras or on braid group should not depend on a braid if the link closure stays the same. So in particular, if you multiply two braids beta and beta prime, the closure does not change if you change the order of the multiplication. So in this picture, you can just slide B prime around so that it now occurs on top of beta. And so this says that Pn of beta prime is the same as Pn of beta prime beta. Or put differently, this trace function, trace n, factors through the coscenter of the finite Hecke algebra. And so another remark that will be useful for us to understand the categorifications that will follow is that Hecke algebra has the following interpretation. So let P be a prime number, Q sum its power, and FQ be finite field with Q elements. Then we can consider finite group of invertible matrices with matrix entries in FQ called GLN FQ. Considers subgroup of upper triangular matrices in it. Then if we specialize V squared to Q in the definition of the Hecke algebra, we get the algebra of B invariant functions on G with the multiplication given by convolution of functions. So in a sense, you can regard Q, the number of elements in a finite field, as a indeterminate some indeterminate parameter, and you recover this definition of Hn in this more geometric way. Okay, so in the next part, I will speak about the categorification of the Homfly PT polynomial. So there is a certain refinement of the trace and so of Homfly PT polynomial that replaces these Laurent polynomials in two variables with a certain triply graded vector space, which is now customary to denote HHH. Well, this is a triply graded vector space, so this is a sum of its graded components, that numbers of which I denote I, J, and K. And by categorification, I mean that you can recover your Laurent polynomial, Jones-Ognanu trace, taking Euler characteristic or Poincaré polynomial and Euler characteristic in one of the variables. So here you can see I sum over all I, J, K and take an Euler characteristic in gradient denoted by K. So this way I get a polynomial in two variables. So this vector space that is attached to any braid is called a Khovanov-Rozansky homology of the braid and of the corresponding link closure, and this defines an invariant of the link. So now instead of coefficients of a Laurent polynomial on two variables, we have a dimensions of a triply graded vector space. So this is strictly more information about the link. However, well, this is a very refined invariant. However, it's usually very hard to compute. And there are now many ways to approach this computation. And in this talk, I will be interested in those coming from geometric representation theory. So in this slide, just some of the categorifications are mentioned. I'm sure there are more. So these are in order or Hochschild homology of Zergel bimodules. So these Zergel bimodules were mentioned by Professor Williamson in his talk. This is a certain algebraic model for the geometric Hecke category. So the way it works, you attach to each braid a complex of bimodules over polynomial ring, and then compute Hochschild homology of the resulting complex. And get some triply graded vector space. So another way to do it is through the machinery of matrix factorization. This is a series of works by Oblomkov and Rozansky. Yet another way, which is partly conjectural, is you can recover the same invariant by computing cohomology of certain coherent sheaves on Hilbert schemes and flag Hilbert schemes. So this was done in the work by Gorsky, Neguts, and Rasmussen. And finally, the most relevant for this talk is computation of this triply graded link invariant through the geometric Hecke categories, which come in two flavors, equivariant Hecke category, and in this setting, the interpretation of HHH was given by Webster and Williamson, and monodromic Hecke category, in which setting this was done by Bezrukamnikov and myself. And these two settings are related by what is known as Kashul duality for Hecke categories. And so in different settings, you can have you can see different features of this link homology theory. So let me spell out more what I mean by the equivariant Hecke category. So now let G be some reductive group. We can take it over C, or we can take it split over some finite field, or we can take it over the algebraic closure of the finite field. There are many different settings in which you can work, and in some sense, many of the results do not depend on the setting. I will maybe say a little bit more about it. So then B is its Borel subgroup. So this is the same in case of G equals GLN. B is just a subgroup of upper triangular matrices. And so equivariant Hecke category is a certain category of sheaves on the double quotient stack G mod B mod B. Or you can say this is a category of equivariant sheaves on G, equivariant with respect to the group B squared, acting by multiplications on two sides. So by the category of sheaves, I can mean, again, many different things. So this will be some sort of mixed equivariant derived category of sheaves on X, wherever the settings is available. So you can take, for example, the derived category of D modules, in which case mixed part will be given by the theory of mixed Hodge modules, or you can take the Linz mixed derived category of L-adic sheaves on X, or if you are willing to forget the weights, you can just work with the constructible derived category of X in analytic topology. So many of the results I will be talking about are not sensitive to this sheaf theoretic settings as long as you have some standard properties of this standard functorial properties. So now I mentioned in one of the first slides that the invariant we're interested in, so it's computed on the elements of the Hecke algebras coming from braids, and it factors through the cocenter of the Hecke algebra. So invariant computed on A times B is equal to invariant computed on B times A. And this has the following geometric interpretation. So we have the following diagram of stacks. We can consider G double quotient by B. We can consider the G adjoint quotient by B. So this is a G quotient by B, where B acting as by conjugation. And we can consider adjoint quotient of G by itself. Then pull-push along this diagram gives a functor from sheaves on the geometric Hecke category to equivariant sheaves on G. And it turns out that this functor is cocentral. So with respect to the convolution monoidal structure on the equivariant Hecke category. So if you compute it on AB, the result is the same as when you compute it on BA. So this CH stands for character. It's called sometimes a character functor. So image of this character functor, by image I mean, for example, a triangulated category spanned, minimal triangulated category spanned by images of sheaves on G mod B, taken as a full subcategory of sheaves on G. So this is known as a category of unipotent character sheaves. These were defined by Lustig and are related to characters of the corresponding finite group of Lie type. So we take G and take it FQ points. The number of different irreducible perverse character sheaves is the same as the number of unipotent representations of the corresponding finite group of Lie type. So now finally, let me say how to compute the triply graded invariant. So in the same way as we attach to each braid beta a certain element of the Hecke algebra, we can attach to each braid beta a certain sheaf, well, a complex of sheaves on the double quotient of G by B. There is a certain natural way to do it. I don't want to spell it out, but this categorifies the way you do it in the Hecke algebra. And the theorem is that you can express Khovanov-Rozansky homology using the following formula. So there is a certain complex for which one can write an explicit geometric formula whose perverse cohomology represent Khovanov-Rozansky homology. So the recipe is as follows: to compute ith part of the triply graded vector space, you take your sheaf F beta, you send it to the group, and you compute hom from ith cohomology of this Xi to the resulting complex. So one important feature of this is that this perverse cohomology of this complex Xi can also be computed explicitly. Well, in some sense, through they can be described via Springer correspondence. So I described how to get one of the degrees, and the remark here says that Two other degrees that we require from the triplet graded link invariant are recovered when you consider the homological grading you get on this derived home, and also the weight, Frobenius weight that you also get. So in this part, it is important that I work with the mixed categories of sheaves. You really need some sort of theory of weights to recover third grading. So some of applications of this abstract looking results are as follows. So this theorem categorifies a certain relation between coefficients of a Hom-Flippiti polynomial to the level of triply graded homology. So recall that, well, our link invariant is a certain Laurent polynomial in two variables, v and a. So we can take a coefficient of this polynomial at a to the power of I, denoted here trace ni. And so it turns out that you really need to know only the zeros coefficient to recover all others. So there are certain linear combinations of braids, EI, which are elementary symmetric polynomials in what's called Juice's-Murphy braids. And to compute I's coefficient of a trace of beta, you really need to compute zeros coefficients of the trace of beta multiplied by this linear combination of braids. So, for example, for the top coefficient, this elementary symmetric polynomial is just a product of Juice's Murphy braids, and this is known as a full twist braid. So you just take all your strands and twist them twice, and so this recovers top coefficient of a knot polynomial through zeros coefficient of a knot polynomial of beta twisted by the full twist braid. And so for this top coefficient, this was done by Gorsky, Hogan, Kapp, Melit, and Nagagane. So I mean this categorification of this relation to the level of to Khovanov-Rozansky homology, and we just extended it to all other coefficients. Another application of this general picture is that Koszul duality for Hecke categories developed by Bezrukavnikov and Yun, building on work of Zergel, Ginsburg, Bellinson, and others. And the Koszul duality for character sheaves in a form that we're developing in this work in progress with Hoyon and Lee implies some additional symmetry for triply graded link homology. It's known as QT symmetry for experts. And this was conjectured in 2005 by Danfil, Gukov, and Rasmussen. And since then, there are different proofs appeared in very different settings. So Gorsky, Hogan, Kamp, and Melit proved it via algebraic means, and Oblomkov, Rozansky in their matrix factorization work. So let me say a few words of how it is done. First, I would like to describe how to lift the statement about the cost center, about the fact that invariant factors through a cost center to the categorical setting. So first of all, it turns out that the center and cost center for the Hecke category are the same. And it's more convenient for me now to describe the center of the Hecke category. And for this, I introduce some more notations. So instead of sheaves on G mod B mod B, I will consider sheaves on G mod U, where U is a unipotent radical. So these are matrices for GLN. These are matrices that are strictly upper triangular with ones on the diagonal, quotient by the adjoint action of the torus. And inside, I consider the subcategory of monodromic sheaves on the same space, monodromic with respect to the projection to G mod B mod B. So this category I denote by H1. This is a certain equivariant variant of the Hecke category. Another category I denote H2 is a square of this category with action of torus twisted in some way, described on this slide. I will not go into much detail for the lack of time. So this equivariant Hecke category is a module over this category H2. And we prove, with Rukavnikov, Ionov, and Warshawski, that endomorphisms of H1 as H2 modules is equivalent to the category of sheaves on G equivariant with respect to the adjoint action of G on itself. And the endomorphisms of H1 monodromic as H2 monodromic module is a category of character sheaves on G. So this should be compared with the following statement about algebras, that endomorphism of A as A tensor A op modules is the center. So here the role of A is played by category H1, and the role of this tensor square of this algebra is played by H2. So in this way, this is a certain variant of the categorical center construction. And the second remark is parallel results were proved by Bezrukamnikov, Finkelberg, Ostrich, Ben-Sveen, Nadler, Lustig, and Holly. So these are all various sheaf theoretic settings and various of this center construction. So all of this fits into the following big picture. So first of all, there is a Koszul duality of Hecke categories. So you can consider, first of all, group Langlands dual to G, which I denote by LG. And then there is a Koszul duality between equivariant Hecke category for the Langlands dual group and monodromic Hecke category for G, which was proved by Bezrukamnikov and Yun. And then this can be used using the result of the previous slide to construct a Koszul duality between categories of unipotent character sheaves on a group and category of unipotent character sheaves on the Langlands dual group. And now, together with this fact that triply graded not a link invariant is categorified by a certain character sheaf, if we can prove that the corresponding character sheaves are Koszul self-dual, this would mean that Koszul duality acts on the corresponding link invariant, and so gives an additional symmetry of this invariant. And this is what we do in this work in progress with Ho, Ionov, and Lee. Yeah, so I have just 1 minute left. I just want to mention two further questions on one can study. One is that many of the features of this picture really hint at the presence of the affine Hecke algebra lurking somewhere in the shadows. So, for example, there is some exotic homomorphism from affine braid group to the finite braid group in type A, which sends what is known as Bernstein generators of the affine Hecke algebra to Justice-Murphy braids that appeared previously. And so this hints that there should be some relationship with coherent incarnation of the affine Hecke category. This is also hinted by this picture with Flack-Hilbert scheme I mentioned in one of the slides. And the second is that proof of the symmetry of triple graded link invariant, Vygotsky, Hogan, Kamp, and Melit, it actually is done in a very different way, not using the Cauchy duality type statement, but using some completely different structure known as curious Lefschetz operators that appears in non-abelian Hodge theory construction and was constructed by Melit earlier. So it appears not directly through geometry, but kind of constructed by hand by them in the combinatorial, algebraic combinatorial world. And so it would be very interesting to see how this structures coming from non-abelian Hodge theory can be manifested in the world of geometric representation theory, in the world of constructible Hecke continuums. Okay, thank you very much for your attention. Дякую за увагу. Слава Україні!